Let us solve concepts of physics textbook problem. A particle having a charge of 2 into 10 power minus 4 coulomb is placed directly below and at a separation of 10 centimeter from the bob of a simple pendulum at rest. The mass of the bob is 100 gram. What charge should the bob be given so that the string become loose? Let us solve this sum. See here. Let us take this is the simple pendulum. This is simple pendulum. Mass of the simple pendulum is m. Here gravitational force mg force is acting and a tension force T will be acting here. Now we are placing a charge here. Let us assume we are placing here charge q, that is equal to 2 into 10 power minus 4 coulomb. This placed at 10 centimeter below the pendulum, 10 centimeter below the pendulum. Now we are going to give charge q dash to this pendulum, so that what charge q dash should be given so that the string become loose. Now see here, this q dash and q charge, between q dash and q charge, here repulsion force should be there. That force is electrostatic force Fe. Here if you draw free body diagram for this bob, mg force is acting downward direction, tension force is upward direction towards fixed point, and the electrostatic force in this direction acting. For string become loose, tension should be 0. That means electrostatic force should balance mg force. Electrostatic force should balance mg force. Now electrostatic force, we know the formula k q1 q2 by r square. K here, q1 is q, q is q dash divided by r square is equal to mg. Actually we need to find what charge should be given to this bob so that string become loose. That means we have to find q dash. Q dash is equal to mg into r square, mg into r square divided by k into q, divided by k into q. Now let us substitute all the values. Here mass is given 100 gram. Let us substitute 100 gram. If you convert 100 gram into kilogram, 1 by 10 kilogram into g value is 9.8 and r value is given 10 centimeter. So 10 centimeter, if you convert into meter, 10 into 10 power minus 2 whole square divided by k value. K value we know that 9 into 10 power 9, and the q is given, that charge value is given here 2 into 10 power minus 4 coulomb. So 2 into 10 power minus 4 coulomb. By solving all this, we will get q dash as that means the charge given to the pendulum is, we get 5.4 into 10 power minus 9 coulomb. So when we give charge 5.94 into 10 power minus 9 coulomb, then the string will become loose. Two particles A and B having charge q and 2q respectively are placed on a smooth table with a separation d. A third particle C is to be clamped on the table in such a way that the particles A and B remain at rest on the table under electrical force. What should be the charge on C and where should it be clamped? Now here given that 3 charges, that means first charge is q, another second charge is 2q. This first charge is q, second charge is 2q. Now we are separated these two charges by the distance d is given. Let us assume third charge is capital Q. When we place capital Q at certain distance, this capital Q also in equilibrium, and this small q and 2q also should be in equilibrium. For that, what let us assume that this q is placed, the third charge placed at x distance from the first charge, so that this third charge will become from the second charge is d minus x distance. First, we assume this third charge to be in equilibrium. For third charge to be in equilibrium, let us assume this is the first charge, this is second charge, this is the third charge. Now let us assume force on the third charge. Force on the third charge is force on third charge by first charge is F1 in this direction, F2 in this direction. We assume force due to first charge is towards right, and force due to second charge on the third charge towards left, we assume. So F1 is equal to F2, then only third charge will be in equilibrium. For F1 to be equal to F2, we will get F1 is KQ1 into Q3 divided by X square is equal to KQ2 2Q into Q3 divided by D minus X whole square. Now let us cancel this k value and small q and this capital Q, all we cancel it. Now see here, d minus x whole square divided by x square is equal to 2. By taking square root, we will get d minus x divided by x is equal to square root of 2. Now listen here, d by x minus 1 is equal to root 2. So that d by x is equal to root 2 plus 1. Then x is equal to d by root 2 plus 1. By taking conjugate in numerator and denominator, by multiplying by conjugate root 2 minus 1 divided by root 2 minus 1, we will get x is equal to d into root 2 minus 1. So when we place third charge, at d into root 2 minus 1 distance, so that third charge will be in equilibrium. Next, we have to find first charge should be in equilibrium. For first charge should be in equilibrium, force exerted by second charge on the first charge must be repulsive because Q and 2Q are like charges. So force on first charge by second charge is repulsive force. Now force exerted by the third charge on the first charge should be attractive. That means the third charge must be opposite sign of the first and second charge. Suppose if you assume first and second charges are positive, then third charge must be negative. Then only this first charge and the second charge will be in equilibrium. So let us assume third charge exert force on the first charge is F13, that is towards third charge. If force exerted on the first charge by second charge is equal and opposite to the force exerted by the first charge on the third charge, then first charge will be in equilibrium. So what is the formula for force? Means k q1 q2 by r square. Force exerted by second charge on the first charge is k q1 into q2 divided by r square is d square we are taking. And the force exerted by the third charge on the first charge is equal to k into q into capital Q divided by, that means third charge, by x square. Now we can cancel this k cancel, and this small q is cancelled. Now by substituting the value of x, we can get the q value. So capital Q is equal to x square by d square into 2q. X value is here, x value we know that d by root 2 minus 1. D into root 2 minus 1. So d square into root 2 minus 1 whole square divided by d square into 2 into q. Now we are going to cancel d square. By simplifying this one, we will get as a 6 minus 4 root 2 of q. And also we know that third charge should be opposite in sign of first and second charge, so that minus of 6 minus 4 root 2 q charge if third charge, and the distance is d into root 2 minus 1, at distance is there, then third charge is first charge and second charge, all the charges can be in equilibrium. Let us solve 28th problem. Two identically charged particles are fastened to the two ends of a spring of spring constant 100 Newton per meter. A natural length 10 centimeter. The system rests on a smooth horizontal table. If the charge on each particle is 2 into 10 power minus 8 coulomb, find the extension in the length of the spring. Assume that the extension is small as compared to the natural length. Listen here. Now let us take a spring. The spring length we assume L. And we are giving two charges at the ends of the spring we are connecting. Here charges are given this q value. This q value is given the 2 into 10 power minus 8 coulomb. As two charges are like charges is there, so that repulsion force will be there, so that the spring will get extended by length x amount. So that total distance between these two charges, that means final length of the charges, becomes actual natural length plus extension. Now due to this repulsion force on the charge, one charge by other charges, electrostatic force, that repulsive force towards the right is there. Due to spring gets expanded, so elastic force will comes into play. That elastic force will be acting in this direction. This elastic force and this electrostatic force of repulsion must be equal and opposite, so that this charge will be in equilibrium. Now let us substitute elastic force and electrostatic force value. Elastic force value is kx. This k, let us take as a k dash. This k dash is known as a spring constant. Spring constant value given that 100 into 100 Newton per meter. This is the spring constant. That is equal to, here F force due to electrostatic force, that is K, Q1, Q2. Q1 and Q2 are equal, so that Q square divided by R square. Distance is L plus X whole square we are taking. Here X will be very small, so that L plus X tends to L. L plus X tends to L we can take. Now we need to find X value, so that X is equal to KQ square divided by X is equal to KQ square divided by this L square into K dash. Let us substitute K value as 9 into 10 power 9 and Q value given that 2 into 10 power minus 8 whole square, and L is given that 10 centimeter. L is 10 centimeter. So 10 centimeter means 10 into 10 power minus 2 whole square, let us take. And K dash given, K dash value is 100. By substituting all the values and solving, we will get this answer as 3.6 into 10 power minus 6 meter. 3.6 into 10 power minus 6 meter is very smaller compared to length or natural length of the spring. So extension in the spring we are getting 3.6 into 10 power minus 6 meter. A particle A having a charge of 2 into 10 power minus 6 coulomb is held fixed on a horizontal table. A second charged particle of mass 80 gram stays in equilibrium on the table at a distance of 10 centimeter from the first charge. The coefficient of friction between the table and this second particle is mu is equal to 0.2. Find the range within which the charge of this second particle may lie. Now let us take what is that means here. This is the table. Here first charge is there. First charge is placed. Let us assume first charge value as Q1. We take first charge value as Q1 we take. This is the Q1 charge. And second charge placed is Q2. This is the Q2 charge. These two charges are separated by the distance given that 10 centimeter. And also given Q1 charge as 2 into 10 power minus 6 coulomb. Here coefficient of friction is there. Coefficient of friction is there. So that what happens means due to repulsion between Q1 and Q2, electrostatic force will be acting. Suppose if Q2 is positive, Q1 is positive, then electrostatic force of repulsion will be there. Suppose Q1 is positive, Q2 is negative, then attraction force will be there. We assumed that here repulsion force is there, so that electrostatic force acts along the line joining radially outward. Here friction force will be acting opposite to the electrostatic force, so that net force will be in equilibrium. Net force will be 0. If we assume what is that means, if charge is repulsive force acting means like charges, positive charge is there. Otherwise, unlike charges means attractive force will be there. So that this Q2 may be positive charge or negative charge. So that answer, when we write answer as it plus or minus, we have to write. Suppose if both charges are we are taking as a positive, then frictional force is acting in this direction. If first charge is positive and the second charge is negative, then electrostatic force will be acting say, towards first charge, so that frictional force to keep the second charge in equilibrium, frictional force should act radially outward. That means away from the first and second charge, frictional force will be acting. Anyway, frictional force is equal to electrostatic force for the system to be in equilibrium. Frictional force, let us take frictional force, maximum frictional force, so that we can get maximum Q2 charge. Maximum frictional force is mu n, that is equal to K Q1 Q2 divided by R square. We know that this charge value, this mass of the charge is m, so that mg force is acting downward, normal reaction acting upward. N is equal to here mg. N value we are getting as n is equal to mg. Since in perpendicular to the table, no motion, so that n equal to mg. Mu value, mu writing, n value we are writing as mg, that is equal to K into Q1 Q2 by R square. Now we need to find range of the Q2. So we get maximum value of Q2. Maximum value of Q2, if you get Q2 is equal to mu into mg into R square divided by K into Q1. Let us substitute all the value. Mu value given here 0.2. So substitute mu value as a 0.2. And mass value given 80 gram. Mass value given 80 gram. So 80 divided by 1000 to convert into kilogram. And G value 9.8. And R value given 10 centimeter. So that 10 into 10 power minus 2 whole square we are converting into meter. Divided by K into Q1. K value we know 9 into 10 power 9. And Q1 value given 2 into 10 power minus 6. Q1 value given 2 into 10 power minus 6. So Q1 value is 2 into 10 power minus 6. By solving all this, we will get Q2. Q2 as a, we will get 8.71 into 10 power minus 8 coulomb. Already we know that this charge Q2 may be positive charge or negative charge, so that answer should be, answer what should be there means for Q2 charge is equal to plus or minus 8.71 into 10 power minus 8. This is the maximum charge, so that system can be in equilibrium. So maximum charge of Q2 is equal to plus or minus 8.71 into 10 power minus 8 coulomb. A particle A having a charge of 2 into 10 power minus 6 coulomb and a mass of 100 gram is placed at the bottom of a smooth inclined plane of inclination 30 degree. Where should another particle B having same charge and mass be placed on the incline so that it may be in equilibrium? Now let us take inclined plane. This is the inclined plane. Let us take this as an inclined plane. Angle of inclination given that 30 degree. Now we are taking two charges. These two charges, one first charge is charge A. Charge A is placed at the bottom, and charge B we have to place at certain distance. At what distance from the bottom the second charge should be placed? That's what question asked. Now listen here. Mg force will be acting downward direction. If you resolve this mg force into two components, one is perpendicular to the inclined plane is mg cos theta, because this angle is theta, and along the plane mg sin theta will be acting. Mg sin theta force, pulling force is acting. Let us assume distance between these two charges A and B as r. Now due to these two charges are like charges, so that repulsion force will be acting. Electrostatic force is repulsive force. This electrostatic force should balance the mg sin theta, so that charge B will be in equilibrium. So let us take the condition that electrostatic force is equal to mg sin theta. Here theta value given that 30 degree. Theta is 30 degree. Electrostatic force we know that K Q1 Q2 by R square. Here two charges are equal charges given. See here having same charge and mass is given. So that KQ square divided by R square. We need to find R only. Mg sin theta. To find R value, R square take right side, so that R square is equal to now see here KQ square divided by mg sin theta. Now let us substitute all the values. K value we know that 9 into 10 power 9, and the Q value given that 2 into 10 power minus 6 coulomb. So Q value let us substitute 2 into 10 power minus 6 coulomb whole square, and divide by mass. Here m is given that mass of the each charge is 100 gram. 100 gram if we convert it to kilogram, so that 1 by 10 into g value 9.8 into this sin theta, sin 30 is 1 by 2. So this all together is R square. Now we want R. By taking square root, we can get R. This R value we will get as 27 centimeter from the bottom. That means second charge B is placed at 27 centimeter from the bottom, so that second charge on the inclined plane can be in equilibrium.